Okay, so hi everyone, and welcome to our webinar on comparative analysis of cell chemistries with JuliaSim Batteries. Um, I just wanted to quickly introduce our speaker today. Mark is the lead developer of JuliaSim Batteries at JuliaHub. He received a PhD from MIT Chemical Engineering, and his thesis work focused on high-performance simulation of physics-based lithium-ion batteries, parameter estimation techniques, and optimal charging algorithms. So I will let Mark take it away.
So thank you so much for the introduction, Ranjan. Today, I'm going to be talking about comparative analysis of cell chemistries with JuliaSim batteries. So today's event is the third and final in a series of webinars. We talked about simulating large battery packs, up to 1,000 cells with physics-based models in the first one. The second one, we showed off some of the JuliaSim Batteries app, or the GUI. We talked about how to quantify downstream uncertainty for manufacturing defects. And today's is the final one in this series where we do comparative analyses with various cell chemistries. So in the world of lithium-ion batteries, there are many potential options that are available to use. You often see these kinds of spider charts, which have a different matrix of different considerations that you might have for various chemistries. So some things like the cost or the lifetime or how much specific energy they have are really important for different applications. But something that's missing from these kinds of high-level overviews of battery chemistries is really the specific application that you're looking at. So something like an EV performance is greatly different than what you would expect in grid storage or in electric scooters. So you can't just look at these charts to try to nail down what specific chemistry you need for your application. You need a really detailed analysis and some kind of way of testing your use case with these various battery chemistries that are available out there. So let's think about a very typical example in the battery world, which is electric vehicles. So the charging requirements for an electric vehicle are pretty stringent. So if you have a supercharger, you need to charge it very quickly because the user doesn't want to be waiting around, waiting for the battery to charge and before they can go on their way. But it also has a pretty unique way of discharging and as well as charging. So these typical drive cycles involve discharging, rapidly stopping and starting the electric vehicle, and regenerative braking, which adds energy to your system. But one other example of how to use a very large pack of lithium-ion batteries is with an eVTOL, for example. So with an eVTOL, you may be able to get away with shorter charging times because you can maybe hot swap the battery, take out the battery after it's finished flying and put a new one in. But the way that you discharge it also behaves a little bit differently. So you have a very stringent requirement for high energy at the takeoff. Once you're in the cruising altitude, it's a little bit less stringent on the amount of energy that's required. And then once you enter the landing phase, you require a higher C rate than, or similar to what you would have during the takeoff phase. But overall, it has a very much flatter appearance in the voltage profile compared to something like a drive cycle. So that's where JuliaSim Batteries comes in. So like we mentioned in some of these previous webinars, JuliaSim Batteries really excels at modeling physics-based cells, modules, and packs. So we base these physics-based models starting with the Doyle-Fuller-Newman model, which is the pseudo two-dimensional model of a lithium-ion battery that strikes a good balance between computational complexity and giving you good performance or good fidelity in your physics-based results. The single particle model, which is reduced order model for this system. And this SPM with electrolyte strikes a balance between these two extremes. So these involve solving systems of coupled partial differential equations, which we solve using the finite volume method as well as spectral methods. Comparing JuliaSim batteries to other tools that are available in MATLAB or Python, we see about a 100x speed performance or speed boost compared to these tools, given the nature of Julia, the programming language, and certain compiler improvements that we've had. And in addition, we have thermal degradation submodels, as well as parameter sets for NMC, NCA, LFP, and LCO chemistries. In addition, you can pretty easily define your own chemistries for use with this system. So you can use JuliaSim batteries to simulate these complex charge and discharge protocols. So in this example, we're comparing the voltage discharge curve of an electric vehicle using an NMC cell. And we can get voltage errors that are less than 0.5%. And because this is running a physics-based simulation, we can get critical safety and state measurements like state of charge, state of health, as well as temperature in your system, which you can monitor throughout the simulation and over the course of the entire lifetime of the cell or the pack. So today we're going to show a few demos using the JuliaSim Batteries app. So first, we're going to show a quick fast charging example using an LCO and an NMC chemistry. Then we're going to show an eVTOL mission profile using LFP as well as NCA chemistries. And from there, we're going to go to a lifetime analysis, looking at 50 cycles of charging and discharging with this fast charging method called boost charging. So let me switch over to the JuliaSim Batteries GUI. And here we have the GUI for the JuliaSim Batteries app. So we have these three physics-based models that are available for our system: Doyle-Floor-Newman, SPM, and the SPM with electrolyte. And we have a few sets of chemistries that we can pick from. So for this first example, we're going to go with an NMC chemistry cell. We can specify the number of cells in series and in parallel. And as well, we can change any of these parameter options in our system, such as the material properties in our negative electrode, our separator, or our positive electrode. So the way that we set up an experiment for this 3C CCCV fast charging simulation is we specify the experiment in our in this tab right here. We give it an initial state of charge, and we can add steps such as the charge, discharge, rest voltage, or power simulations. So here we're starting with this 3C charge with an unknown final time. And then once we hit the maximum voltage, we enter the CV hold for 300 seconds. So we can hit the run button. And after a few seconds, we can get the results for our simulation. So we see right now we're plotting the C rate, the voltage discharge curve. But we can also plot other metrics such as the power or the state of charge for our system. We can also go in and we can very quickly and easily change the chemistry. So if we want to change it from an NMC chemistry cell over to an LCO cell, all you have to do is go to this chemistry preset, click on this dropdown, select our new chemistry, and hit run. And in a matter of seconds, we get the results for our new lithium-ion chemistry cell. So you can see we get a pretty different charge protocol for our C rate. We have a different power curve, and we can view all the various metrics that we have and want to analyze for our system. So one way that we can extend and compare some of these results with one another is we can save the entire simulation results. So this, it stores the battery configuration, It stores your experiments that you have specified, as well as the raw data for some of your plots that you have here. So all you have to do is click save. And just like we had the save, we can also import it. So moving on to the second step, we can import a new file for our system. You can see right here we have this saved file which I just created. But for the second part of this, we're going to look at an eVTOL discharge protocol using an LFP cell. So all we have to do is open, click import, and there we go. We changed all of our experiments, we changed our initial SoC, and we're now looking at a new discharge protocol for our eVTOL system. So with this system, we have an initial discharge C rate of 5C for 100 seconds, which represents the takeoff portion of the mission profile. It's followed by a discharge of 1.5C for 800 seconds, representing the flight of our eVTOL. And then the third and final step is this landing sequence, where we also require a reasonably high C rate for 100 seconds. So we also changed the chemistry of our system. Additionally, we have these thermodynamics that are enabled, and we can view all the various material properties and parameters that we specified for our system. So all we have to do, again, is just hit run for our new simulation and visualize the results. So now we can see for our eVTOL system, we have this 5C discharge, the 1.5C charge, or sorry, 1.5C discharge for 800 seconds, and then the final 1.5C discharge. So we can view other metrics. We don't just have to look at power or state of charge. We can look inside the battery and in the electrolyte. We can view these electrolyte concentrations, the electrolyte potentials, and this shows you a 1D plot going across the length of the cell, starting at the left here from the anode to current collector interface, moving through the separator, and then over to the cathode to current collector interface. Additionally, we can change this time slider here, and that represents this red dot, which affects the plot for these 1D simulations that we have here. So we can see that after about 50 seconds of charging, we can see the variation of our electrolyte concentration within our system, as well as the polarization that we get as a result of our electrolyte potential. We can move this into the 1.5C region, and we see a much less drastic effect. And this is because we don't apply as great of a current density to our system. One interesting thing we can look at is this very flat and characteristic voltage discharge curve that we get from an LFP type cell. And we can also, just like we did in the other experiment, we can swap out what chemistry we're using. So from an LFP cell, I'm going to swap it over to an NCA cell. And all you have to do, hit run, and in a few seconds or so, we can get a brand new simulation showing all the results for our system. We can look again at the various charge and discharge protocols, we can look at the electrolyte concentration and see how these parameters and how the various chemistries affects our system. So for the third and final example, I'm going to show a boost charging example. So this is starting with a C/2 discharge, and we repeat this simulation for 50 cycles. So what boost charging is instead of the conventional CC/CV charge that we see very common in lithium-ion batteries, we start it with a very short 60-second voltage impulse starting at the maximum voltage. So we specify this voltage profile of 4.2 volts for 60 seconds. We follow it up with a 2C charge, and then we end it with a voltage hold until we reach some minimum current. So We can go back to our configuration, see we've enabled the SEI degradation, as well as our thermodynamics. And all we have to do is hit run. And just like we had for the other experiments, in a matter of seconds, we can see the results for 50 entire cycles of a charge and discharge protocol. So right now we're viewing the the full cycle for one full discharge and charge protocol. Just to zoom out a little bit, we can look at some metrics like the cycle life. So here in this blue dot, represents the current state of health at that particular cycle. And you can see we get about 2% capacity fade over these 50 cycles. So we can zoom into specific discharge as well as charge points in time. We can change the cycle number, and we can see how it affects the various metrics in our system. We can change this over to the charge, where we see this pretty extreme charging protocol and pretty unusual. So with JuliaSim batteries, because it's so robust, we're able to simulate it starting at C rates of 55C, which is really difficult to do numerically and is a common pitfall in a lot of these battery simulation tools. So right now, we're using an LCO cell. Just like we did before, we can swap it out over to an NMC cell and see how does it affect the performance once we change our chemistry. So again, we're running this on JuliaHub. It's our cloud computing platform. And just in a matter of seconds, we're able of completely simulating the 50 cycles of our system. We can see the different performance. We can measure all the various states and the outputs. If we want to save these results, either for the very particular result here, we can save it as a picture or as a CSV, or we can take a view of all the plots that we have here in our simulation for use later. Okay, so maybe I'll pause here and see if there are any questions.
Yeah, so I think there's a question here on, if parallel and series connections, how parallel and series connections are realized from a modeling perspective, and yeah, is it a full PDE for each cell, and so on. If you could comment on that.
Yeah, so maybe I'll start with the PDE question. So yes, for each cell, we're using the DFN model here. There's about 5 PDEs that we have, and we're solving simultaneously for each cell. So these are PDEs for the electrode concentrations, these porous electrodes, of the electrolyte concentrations, as well as the electrolyte potential and the solid potential that we have for our system. If you include temperature, that adds another layer of complexity there. So yeah, these are all being solved in real time on JuliaHub cloud computing platform. So the second question was about how do we connect these in series and parallel, correct? So the way that JuliaSim models these systems, so in JuliaSim, these batteries are just a component with one negative pin and one positive pin. And just like you would connect up a battery pack in real life, where you connect the pins to each other to make sure that they're connected in a circuit, you do that in code with JuliaSim batteries. Yeah, so it's just as easy as specifying the connections between cells. But this is all handled under the hood. All these calculations like ohm laws, they're all just built into the modeling logic. So you don't even have to worry about that.
Cool, thanks, Mark. Any other questions for Mark at this point? I don't see any, so you can go ahead, Mark.
Okay, let's jump back into the slides. So, using these various chemistries and the results that you can save for each of these simulations, you can generate things like very long-term charging and discharging protocols for your system, including cycling them all the way until they reach the end of life, which is represented by this 80% state of health red dotted line that we have here. So these take a little bit longer to do, around a few minutes or so using JuliaHub. But these kinds of analyses are really powerful because they let you see what kinds of chemistries are going to lead to long-lasting batteries for your system. But if you have different requirements, such as faster charging systems, you can see very different results based on the choice of degradation profiles that you specify. So you can draw really powerful conclusions in just a matter of minutes, all in simulation using the JuliaSim Batteries app. So one of the big things about JuliaSim is incorporating this idea called scientific machine learning into our models. And it's where we take these well built and justified foundational physics-based models, like the DFN model or the SPM, and we say, okay, there's a few parts of these models that we don't understand quite so well. So these can be the low temperature regimes in lithium-ion batteries, or maybe the degradation profile. And you can take your equations that you've specified, and you can combine them with machine learning models to try to learn some of this unknown behavior. So that can include these degradation methods, as well as things like the electrolyte behavior, or really any like diffusion in the system. It really depends on what you want to learn and what kind of data that you have available to train these neural networks for your system. So one example of this is work that JuliaHub and CMU collaborated on, where they took real data from simulated eVTOL batteries, and they compared the foundational simulation, which is represented by a physics-based battery model, and they tried to learn the degradation profile using these scientific machine learning tools, and they did that with data. So they found that they can predict and figure out what are these degradation protocols pretty well and extrapolate them all the way to very early and very late parts of the battery life cycle. So another important part of JuliaSim batteries that we've mentioned in a few of these previous webinars is modeling some of this like manufacturing variation, which you can see affects the lifetime of your system. So this example that we have here affects the state of health as we change just a few key parameters to your system that we get variation in the manufacturing region because of. So these are some of the thicknesses of your electrodes, as well as the separators, as well as some of the active material coatings that we get on the electrodes. And with just these very few changes in the system, we can see that we get a really huge variation in our lifetime. So as we know, not all cells are created equally. So we really don't need, or we really need a modeling platform that can support, not just simulating one cell behavior, but a wide range of cell behaviors to make sure that, you're not just looking at individual cells, but looking at the entire batch performance that you can get and see things like what is the potential warranty that I can specify for my system. And this allows you to take use of all the other tools that we have in JuliaSim batteries, like these complex charge and discharge protocols. And for example, here, we're looking at, again, a fast charging CC-CV charging sequence. So with that, JuliaSim Batteries makes these analyses and comparisons of cell chemistries really easy. You can use the JuliaSim Batteries app, which is available today, to get really deep insights into these analyses. So we can simulate these very complex and demanding performance curves, like this eVTOL mission profile, rapidly in just in a matter of seconds using the platform. And additionally, you can export and save and interact with all the information that you get using the JuliaSim Batteries app. So, you can use it as a tool to really empower your team, empower your workflow to get the most out of your batteries. So if you're interested in working with JuliaSim Batteries or JuliaHub, we have a short-term pilot engagement program. So if you want to optimize JuliaSim Batteries for your particular use case and you need some help getting started, we can work with you to calibrate a cell exactly to your chemistry and your data and make sure it scales all the way to the pack level for your system. We can give you training, documentation, as well as the ability to generate custom reports. And in addition, this comes with a dedicated JuliaHub cloud computing environment that's SOC 2 compliant. If you're interested, you can contact us on the email at the bottom, to sales@juliahub.com. So with that, I thank you for your attention and happy to answer any remaining questions.
Woohoo! Thanks, Mark. So, I'll read out a few questions here, but for the rest of the attendees, feel free to, keep those questions coming. The first one is the role of machine learning to discover, to discover and then model behaviors in the empirical data that are not produced by the physics-based model.
Yeah, so that's a good way of stating it. So there are certain parts of the model that physics and even the top theorists can't really write down exactly what's going on there. So we use the data and the machine learning to figure out in these key places where we don't have all the answers, what can we model and how can we get that to work based on your data.
Okay, thanks. With your current degradation models, are you able to predict when the knee or a cliff in cycle life may appear for a given cell model?
Yeah, so that's a good question. So in these examples that we have now, we're just using this one SEI capacity phase model. So usually or in some cases with the knee analysis, it becomes apparent when you've reached like some secondary stage of degradation. So like you have the initial, maybe linear type degradation, and then there's a second wave of degradation. So we're working on expanding our degradation modeling. It's something that's actively going on with JuliaSim batteries. So this is certainly something we're interested in modeling and capturing. But additionally, if you, for example, have data on the knee points analyses or some of these state of health measurements that you want to model, we can work with you to incorporate some of this into the models that we have available.
Cool. The next question is, can this be used in an online framework? For example, if I want to control for a certain state.
Yeah, so I think we can. So it would probably have to be done using the code. Um, maybe we can follow up on that. I'm not a controls expert, but there is a JuliaSim controls entire toolbox that we have, which is built exactly for this purpose. So I'm sure we can, take some of these JuliaSim battery models and, plug it into the controls interface and, get pretty complex, control algorithms built in.
Cool, thanks. And just a reminder to attendees instead of raising your hands to put your questions in the chat. Um, The next question is, can you discuss which components of this demonstration use open source code and which components are proprietary code?
Yeah, so it's a good question. So the battery, the JuliaSim batteries, that is a proprietary code base. But in making JuliaSim batteries, it uses part of this ecosystem called modeling toolkit. So modeling toolkit is a way of expressing um, various connections and building of physics-based models. It includes thermal and electrical libraries, both of which are in JuliaSim batteries. So you could, for example, hook up JuliaSim batteries with some of the open source and available thermal properties that are available in like the modeling toolkit standard library. We also have an HVAC library, which is proprietary. And these things can be easily hooked up and connected together to get pretty complicated performance. Um,
Cool, thank you. Except for the GUI, are there improved bits from this model compared to PetLion?
yeah, so maybe for the audience here. So Petline was a project that I wrote in my grad school days, which is an open source DFN simulator. Um, so yeah, there are a lot of improvements. So for example, the ability to scale to any size packs, that can't be done with PetLion, and a lot of other tools that are out there can't really scale to the pack level with any physics-based model. There's many more models that are available. So PetLine is limited to the DFN, but you can use the SPM and the SPME with JuliaSim batteries. There's this whole idea of like connecting other systems together, like saying connecting a battery pack with an HVAC system. And that's like a first class component of JuliaSim and of JuliaSim batteries, but there's no notion of that in PetLion or many other battery simulation tools for that matter.
Well, um, if a new battery chemistry is developed, are the are the model internals exposed enough that I can independently create the model for the new battery chemistry with JuliaSim batteries?
Yeah, so it depends. So if you wanted to, like, say, add a new OCV curve or a new diffusion in your electrodes, but you still want to maintain like the same structure of like a lithium ion cell, that is something that can be done today without having to expose any of the internals of JuliaSim batteries. There are other parts though, such as if you wanted to, I don't know, add another electrode in your system or add like a reference electrode or something, where that would be, you'd have to do that through the internal code base. And I think as of this moment, we are not exposing that to the users.
Okay. With the GUI, can parameters be added as a function? For example, lithium diffusivity is a function of stoichiometry.
Yeah, so that's one limitation that we have as of today, but it's something that we're actively working on and will be there very soon.
Cool. Um, let's let's see if there are any more questions. Da, da. There was one question about the GUI development and whether it was built in Pluto. Um, uh, just for context, for all the other attendees here, Pluto is a notebook system that's implemented in Julia and hosted on JuliaHub, and this is something that a lot of our customers used to share work with each other. This, however, is a full sort of design and analysis app, which is independent of Pluto. So just wanted to put that out there. for folks. Maybe we'll wait for 1 more minute to see if there are any questions. Otherwise, we can go ahead and conclude. So I'll just wait for another minute here. Okay. Okay. You said that there are many other modeling frameworks that aren't able to handle pack level. Could it be said that there is not any other framework?
Yeah, so I mean, for physics-based models, there's no other framework that can handle thousands of cells and still get anything close to real-time simulation. So what many of these other tools do is when they scale to the pack level, they throw out the physics and they swap in like an equivalent circuit model or some kind of empirical battery model or some lumped pack model to try to achieve something close to real-time performance.
Cool. And riffing off of that, if let's say I was a customer and I wanted equivalent circuits, right? Like, is that, for various reasons, I want to maybe evaluate this model very, very quickly, a large number of times. Is that something I could do with JuliaSim batteries today or tomorrow? If you had to comment on that.
Yeah, so we're working on adding equivalent circuit models. Like you said, mostly for comparison purposes, and if you really need crucially real-time performance for your system, it could be a mess.
All right. And the final question is, are recordings of the first two presentations on this topic available? The answer is yes, and we can get them to you. If you go to our website as well, which I will link in the chat, you should be able to sign up and get those recordings. So I'll just send a link to the chat there for where you can find our previous webinars. So the next question is it because of Julia that that this pack level real-time simulation of DFN could be achieved, or is it SciML? Can you expand?
Yeah, so this is we talk about this in the first webinar in this series. We go into some detail on this. But in short, we've developed this proprietary compiler, which works to, leveraging Julia, but is hyper specialized for simulating repeated components that you can have in a system that, for example, you see in like a battery pack with thousands of very similar cells, all having maybe different parameters representing like cell-to-cell variation, but still the overall structure being the same.
Yeah. Maybe in our post attendance email, we can send you links to the other two battery webinars as well for the attendance. But as of right now, I've just shared a link where you could find them on our website. Um, so I think we're at about the 45-minute mark. Yeah, I don't see any other questions. So I'll thank Marc for his time and thank all the attendants for their time as well. And yeah, have a great day, everyone, and thank you for joining this webinar. And hopefully we'll stay in touch soon.
Thank you.